Linear discriminant analysis in Navure. Linear discriminant analysis, LDA, is a statistical technique used to find linear combinations of features that best separates different classes. It projects data into a lower dimensional space, named discriminant space, by maximizing the difference between class means and minimizing the within-class variance. We will demonstrate how to use linear discriminant analysis in Navure with the IRIS dataset, a widely recognized dataset created by British biologist and statistician Sir Ronald A. Fisher in 1936. You can find this dataset in the test data repository, consisting of 5 columns. The IRIS column contains the names of 3 plant species, while the other 4 columns represent the petal length, petal width, sepal length, and sepal width values for 50 flowers of each species. Once the data file is open, click the Multivariate tab and click the LDA button. Select all numerical variables and drag and drop them into the Numerical Predictors panel. Then drag and drop the IRIS variable into the Class ID panel. Now click on the green Play button, which will apply the default settings. Other settings, found under the blue Play arrow, include which additional tables to display, the number of discriminant dimensions to extract, and the number of iterations of the cross-validation loops. Important: when you initiate a classification procedure for the first time, Navure may request permission to access both public and private networks. This access is essential as Navure utilizes parallel computing to enhance performance, especially for random forest and upcoming procedures in subsequent releases. Please grant the necessary access to ensure proper functionality. You or your IT manager can always configure the firewall to allow Navure access to these networks. Remember that LDA creates a new space, the discriminant space, by linear combining original features, flower measurements in this example, to maximize separation between classes, species in the example. The first table displays the normalized contributions of each feature to the construction of the first and second discriminant dimensions. We can see that petal length has the highest importance for the first discriminant dimension, as indicated by its highest absolute value, followed by petal width. Notably, both variables play a significant role in both the first and second discriminant dimensions. The second table shows the performance of the classifier. An accuracy of 98% means that 98% of the cases were correctly reclassified. This accuracy is calculated from the average of multiple cross-validation loops and provides a reliable assessment of the classifier's effectiveness. It's important to note that in classification problems, the training data set used to instruct the classifier should contain a significant number of observations in each class. This ensures the ability of the classifier to handle new cases. While cross-validation techniques improve our ability to assess the robustness of the classifier, the quality and size of the training data set remains critical. The third table is the confusion matrix showing the hits, main diagonal, and the misses outside the main diagonal. Out of the 150 cases, only 3 were misclassified. The fourth table is the confusion matrix expressed as proportions of the original classes. For the sample, all setosa data points were reclassified as setosa. For versicolor, 96% were well reclassified and 4% were misclassified as virginica, and 98% of virginica were well reclassified and 2% were misclassified as versicolor. Finally, a bitplot that illustrates data points colored based on their reclassification, superimposed with a representation of variables derived from the standardized discriminant function coefficients table is shown. The bitplot displays variables on a hidden scale that accurately reflects their coordinates in the standardized discriminant function coefficients table. This visualization effectively combines information about data point reclassification with the positioning of variables in the standardized coefficients table, providing a comprehensive view of the relationship between variables and their impact on classification. Please be aware that in the bitplot, the coordinates of the data points, often referred to as discriminant scores, are presented as additional columns in the data table, along with the classification assigned to each data point.